It's my pleasure for me to introduce the speaker of this week, Yalçin. He is an associate professor at the University of South Australia, where he has joined in. He has joined since 1996, right?
Yes, correct.
And, yeah.
Ages ago.
And Yalçin also has visiting position in several places over the world. For example, in Brazil, in Turkey, in Germany, in Austria, in Canada, and US. Yes. Yalçin, now it's your turn.
Thank you very much, Min. Well, thank you for the invitation, the opportunity to give this talk. Unfortunately, I had to miss the past, the previous 8 weeks talks, which were all very interesting, but I had to teach at this very time, same time as the time of the seminar. But now I'm able to, I have time because we are in teaching break last week and this week, and from next week onwards, we will have 5 weeks of more teaching. So I apologize from those speakers whose talks I couldn't attend before. I will talk about projection methods for some class of optimal control problems. This is joint work with Heinz, Bauschke and Regina. The early part of my talk depends on something that some work that we published before. It was specifically dealing with the optimal control or minimum energy control of the double integrator. In this case, I will consider first the cubic curves in Rm, which is a generalization of the classical double integrator. And we'll talk about how we do constraint splitting and projections. Then introduce, not in detail, just algorithmically, the 5 best approximation algorithms: Dykstra, method of alternating projections, Douglas-Rachford, Aragón Artacho-Campoy, and FISTA. We'll present numerical experiments, and we'll look at parametric behavior of some of these algorithms, which those algorithms which depend on certain parameters, and look at do a numerical error analysis, and at the end see which of these methods will work reasonably well, relatively better for the type of problems that we will be considering. Well, the main motivation for this is when you look at the literature, Douglas-Rachford method you see being applied to optimal control problems, but only in discrete time. Well, optimal control problems are given traditionally in continuous time. So you have an objective functional subject to a system of differential equations, ODEs or PDEs. But it is not possible for us, at least, to see any application of these projection type methods to continuous time optimal control problems. So that motivated us to start looking at that. And we have published this one particular paper where we considered a very special simple case of an optimal control problem. And another motivation is that although the statement of the problem looks much simpler than many other optimal control problems, the minimum energy control of the double integrator in Rn, I mean, it covers the curves, spatial curves in R2, R3, or in higher dimensional spaces. It's a building block for cubic splines, because cubic splines problem is specified in exactly the same way, with the exception that rather than going from one point to another, okay, you do the same, but you have to visit a set of other points in between. So we pose the problem of finding a cubic curve in Rn as the problem of minimizing the average length of the acceleration of the curve. U is the acceleration, so x2 is the speed, and x1 is the position. But when you find x1 of t, that's your curve. So this average acceleration, I said, you can express it as the L2 norm, squared L2 norm of the acceleration. Length of the, it's possible to replace this, of course, with other measures like L1 norm or L infinity norm. Each time you look at these different problems, then you get different types of curves. But cubic curves are particularly attractive because they can be readily implemented for dynamical systems, obeying Newton's second law of motion, like drones or underwater vehicles or spacecrafts. So where you have this Newton's second law of motion, the giving the governing equations, in that case, it is attractive to minimize the acceleration vector. It is to do with the motor or the engine of the vehicle that you are doing the driving. In this model, x1, as I said, position, x2 is the velocity. They are referred to as the state variables. And u is the control variable. And more specifically, we can break up the vectors into components in this way. When n is equal to 1, then it's traditionally the minimum energy control of the double integrator. But the shouldn't be written double times here. And for n equals 2 and 3, you get spatial curves with minimum average acceleration. It is interesting here to consider a constraint on the length of the acceleration. It makes sense because I talked about engine or the motor of that is being driven, which you will want this vehicle to follow the path that we are going to be designing. Well, it makes sense to put a constraint because this constraint might be given by the specifications of the vehicle, or you may want to operate in along the path that you will be optimally designing, to have as small, as light a motor as possible. For n equals 1, we can think of a car doing rectilinear motion. For n equals 2, we can think of a spatial curve in R2 in the plane, where we are given the initial and terminal points as well as the initial and terminal slopes of the curve that we are trying to construct. For n equals 3, well, then you can try to visualize this in R3. Imagine that we have a drone here with certain velocity, and from that instance, you would like to get that drone in 1 unit of time to another position, in this case, to another height, and having a velocity which is given in this direction and magnitude. So these are quite real-time problems, and With the constraint that is imposed, they become non-trivial problems to solve. It's important to solve these problems not only accurately, but in a short period of time. So this is an investigation to see if projection methods will allow a viable alternative to existing ones, because as I said, projection methods are not being used for these kinds of problems, and see if we're going to get any advantages. Okay, going back to the minimum energy control of the double integrator, okay, imagine a mass, unit mass, so which we are deriving by the force U. Initial position is given as S0, terminal position is given by SF, initial velocity V0, and terminal velocity VF. So it moves back and forth, and in the meantime, we would like to minimize in driving this system from S0 V0 to SF VF, at the same time minimizing its energy, because this average acceleration is related with the energy of the system. We can write down the solution. This is textbook exercise. We can write down the solution directly for the control variable and state variables. There are these constants appearing. Those constants can be written as well. By the way, I mean, if we rewrite this problem, not necessarily for this R1 example, but for Rn, in which case U squared here will be replaced by the norm of U, squared norm of U being integrated. And X1 will be in Rn, X2 will be in Rn, and U will be in Rn. The solution you get is exactly the same as this, where C1 and C2 this time will be constants in constant vectors in Rn. So it's really straightforward. It's very easy when there are no constraints. Okay, we can view the solution here. One thing to note here is that U is linear. Velocity, the integral of the acceleration, is quadratic. And the position, the integral of the velocity, will be cubic in time t. What happens when we impose constraints on the control? As I explained, it's really sensible for many reasons, practical especially. So we need to refer to the maximum principle, in which you form the function, Hamiltonian function. We write down the integrand of the functional that we want to minimize, and append the right-hand sides of the differential equations by means of these multipliers lambda 1 and lambda 2, which are referred to as adjoint variables or co-state variables, and they are defined to satisfy these equations, differential equations. Partial derivative of h with respect to x1 is 0, and the partial derivative of h with respect to x2 is lambda 1. So lambda 1 dot is equal to 0, and lambda 2 dot is equal to lambda 1. It gives us lambda 1 to be constant and lambda 2 to be a linear function. So this is something we want to be satisfied, so that maximum principle can be stated here, which says that if U is an optimal control of the problem that we pose, then there exists a continuously differentiable vector of adjoint variables, lambda, and these lambdas is a non-trivial vector function for all given time. Then U is a minimizer of the Hamiltonian, and U is given then as the minimizer of this 1/2 V squared plus lambda 2 V, which can be solved simply as follows. Okay, when lambda 2 is between minus a and a, we have minus lambda 2. If lambda 2 is less than minus a, then u is a. If lambda 2 is greater than or equal to a, then u is negative a. So we note here that the optimal control u for problem P is continuous, but not differentiable at the junction points in general. So there are several approaches for solving numerically this problem. The first approach is first discretize, then optimize. How does it go? You discretize problem P directly, right from the beginning. Like what exists in the literature. You know, people look at the time discretized optimal control problem using projection methods. It's been done. But if you're not using projection methods, you may use some established software. Ample is an optimization modeling software. IPOpt is optimization software. You combine them, you can very simply write a code and pair it up with IPOpt and get a discrete approximation of the state and control variables. So this is one approach. But we have to keep in mind that this is not necessarily the R1 example that I've talked about. It could be the example in Rn, and this can be quite onerous because the dimension grows immensely. I mean, the time discretization that you take is typically thousands for X and U to be fair, you know, reasonable discretizations. So for reasonable solutions, then the number of variables easily go to thousands of variables. So we are talking about very large scale problems immediately. But one advantage of it, of course, the subproblems that one typically deals with in an optimization method, they become sparse. There's an advantage, but still it is quite challenging in general obtaining these discrete solutions. Another approach is first optimize and discretize. In that case, we write down the conditions of optimality from maximum principle. And then we solve the equations and inequalities given by the optimality conditions by using other techniques like you have the you know, variational inequalities, for example, that you would deal with, then that goes into the second type of approach. If you have no constraints, then you typically have a two-point boundary value problem, and you would solve that by using Runge-Kutta techniques. That's also not easy. That's also not easy. Then you will still have to deal with discretize. You will have to deal with a large number of variables. Another approach is arc parameterization if your solution has certain structure. I mean, I've just shown that the solution, when you look at this, it consists of three types of arcs. One type is when U is constant, A, or negative A, or it is a linear function, lambda 2 is linear, we saw in T. So in Rn, of course, I mean, U of t is not equal to A, but in that case, it is A times lambda 2 of t divided by the norm of lambda 2. So in that case, you are projecting on the sphere, because here then V norm of V, L2 norm of V is less than or equal to A. That's how we write this in that way. Then the minimizer of this expression here, in the case V is a vector, is nothing but a vector living on the sphere. But still, there is structure. So it is attractive. I mean, it is it is tempting to use that structure. And in the case of a scalar U, so parameterizing with respect to the concatenation of these types of arcs for the unknown junction times, for the unknown junction points. And then you will have a small number of variables, and you can use some optimization software, again, ample plus IPOpt, for the unknown junction points. So these are three typical or classical, let's say, approaches that one may employ in solving the problem that we've just posed. However, we will try something new. We will try something. We will try projection methods which haven't been used before. So the analytical solution. Okay, here we can write down the analytical solution for this special case easily, and the numerical solution for the constraint case when A is 2.5 and you're going from 0.0 at rest at velocity, sorry, not at rest, 0.0 with 1 unit velocity initially. Eventually it will travel and then bring it back to where you started at rest and come to rest. So that problem is solved, can be solved analytically in this way. And we can see that optimal control consists of 3 arcs here. One is negative A, and then linear function, and then positive A. And that's determined by the multipliers lambda 1, lambda 2. And it's possible to double check the numerical solution if it satisfies at least the first order necessary conditions of optimality. Here, we can easily check that when lambda 2 is positive, then U is negative A. When lambda 2 is between negative A and plus positive A, then it is U is simply negative of lambda 2. And when lambda 2 is negative, then U is projected to A, the constant. So in optimal control, when we do numerical computations, it's also our job somehow to come and check these conditions, because we solve the problem as a finite dimensional optimization problem, but does it really satisfy the conditions which are given in function spaces, using functions in infinite dimensional spaces, in other words? So that will be another line of thought for us when we do the projections. Before doing the projections, of course, what are we going to project? What have in mind projecting? So we have a bunch of constraints. We split the constraints into 2 groups. One group is the one involving differential equations for x1 and x2, including the initial and terminal points. And the second constraint that we consider is the constraint on U. This is for R1, of course. When it's in R2, then we have this. I mean, this is the only difference, and it makes the problem becomes more rich. Like, rather than considering a closed interval, then we are considering a ball for the vectors U in which they lie. Okay, so we call the first constraint as A, curly A, set of all these functions U that satisfy the 2-point boundary value problem, if you like, here, x1 dot equals x2, x2 dot equals U, subject to these initial and terminal points. So it's a 2-point boundary value problem, and set of all these U's is giving us curly A. And you may ask, well, do you guarantee a solution? Yes, we do guarantee a solution because the problem is unconstrained. That's the beauty of it. I mean, unconstrained, these are constraints themselves, but in optimal control, usually, okay, you have ODEs and you want to minimize something, some functional. That problem is referred to as an unconstrained optimal control problem. And you can rather easily solve that. When you impose constraints, then things become difficult. In this case, the only thing you need to look at is if the system is controllable. That is, by changing U, can you change X1, X2? That is, you start at S0, V0. Can you find a U that will take you to SFVF? Yes, you can. But because by varying U, you can vary X2 and X1. This is the practical explanation of it, but more technical and proper explanation of it is that you satisfy a Kalman controllability condition. That the system is controllable, that is, you can drive it from any given point to any other point. And set B is rather simple. It's the set of all U's which are in the ball given by the L2 norm of U less than or equal to A. We note that curly A is an affine subspace and B is a ball. So we get we have a convex setting. We define the projections as one of first projecting onto A. How do we do that? But we minimize the distance from the current iterate or wherever we are in the control space. We are at some point, so we project it onto a point in curly A by minimizing the distance, but this distance between where we are and the points in A, the set A, that is, we choose the closest point in curly A to the current point where we are in. And the second projection is projection onto B. In that case, we consider all U's in B, in the ball, and then we minimize this. So the first problem needs a little bit more care. The second problem is rather straightforward. If you're inside the ball already, then your solution is U itself. I mean, you stay in the ball. If you're outside the ball, then you simply project it. Projection is very easy to write. But let's look at the projection first one. But this needs some couple of pages of proof for saying that the projection on to A is the point where you are currently plus a linear function, which is nice. Where the C1 and C2 are given slightly differently from the C1 and C2 we wrote before. They are different. And the X1 of 1 and X2 of 1 that are appearing in the expressions for C1 and C2 are obtained by solving the initial value problem here. This initial value problem, okay, suppose that you started with U minus equals 0, then you do iterations, and turns out that you have a piecewise linear function. So you are solving here not quite a linear differential equation, but nonlinear differential equation, but this U minus is of special form, which is piecewise linear. So at least to have a handle, well, we can apply just Euler's method here, not any other method like midpoint or trapezoidal or higher order Runge-Kutta methods, because Here, the right-hand side of the of this equation is not differentiable. I mean, at points it will have be broken, this u bar. So Euler's method seems to be an appropriate way to approach that. For the second projection is what I've just described. If you are in the ball, then it's the function itself. If you are outside the ball, you just project the vector onto the ball of radius A. So projections are good news. In fact, that's what motivates us to use projection methods. Projection methods, I mean, as far as we can see from all the other applications in the literature, they are interesting if you can simply project to these subsets or into these separate split up constraints. So we have that here. And best approximation algorithms that we have considered, the space for in which they are applied is a real Hilbert space with appropriate inner product and norm. And this A, not curly A, general A, is a closed affine space of X, and B is a non-empty closed convex subset of X. So in our case, curly A and curly B fits to this description. So given Z in X, our aim is to project this Z to the closest point in the intersection A intersect B, which is non-empty. Okay, in this setting, okay, we take X to be the L2 space because we consider curly A and curly B to be A and B. We consider initial starting point, the point where we start as 0, and we consider 5 methods. The first one is Dijkstra's algorithm, which was proposed and shown to be strongly convergent in the spaces that we consider. A method of alternating projections goes much earlier, first studied by von Neumann in 1948 and shown to be convergent for affine spaces. And then Bregman showed that for closed convex sets, it's weakly convergent. Douglas-Rachford algorithm, which has been shown to be weakly convergent as well, proposed and studied by Douglas-Rachford in 1956, Léon Mercier in 1979, and we also point to Eckstein and Bertsekas in 92. There is one new algorithm which can be regarded as some extension of the Douglas-Rachford algorithm. Aragón Artacho and Campoy, which we call Aragón Artacho-Campoy algorithm, or AAC, is being shown to be strongly convergent under some constraint qualifications, which are not straightforward to check, at least in our setting. And the last one is an approach which is very popular recently, in recent decade or so. Fast iterative shrinkage thresholding algorithm, or FISTA, which was shown to be strongly convergent by Atouche and Cabot in 2018, well proposed by Beck and Teboul, but on iterative shrinkage thresholding algorithm to make it fast using an acceleration term by Nesterov. Okay, Dykstra involves normally, okay, some initial iterates of the algorithm, and two auxiliary variables, two auxiliary vectors that we update as we go along, P and Q. P boils down to 0 because one of the constraints is an affine subset, one of the constraint sets. But Q survives, and that gives us an algorithm which is different from method of alternating projections. In the method of alternating projections, you get that by simply deleting Q's from everywhere. And you project first onto B and then onto A. And we have a stopping criterion based on what we get in A, but we get U tilde, the projection onto B. It makes more sense because, you know, for the control to be viable, to be feasible for the real problem, we should really get the projection onto B in all of these algorithms, in the previous one as well, so that it is a feasible control for the optimal control problem. Okay, that's one small twist, let's say. And there is a version of Douglas-Rachford algorithm here involving a relaxation parameter lambda. When algorithms involve a parameter, then really it's a bit tricky how to choose the value of that parameter. With the value that we use is 0.7, which we found in the paper that Heinz, Regina, and I published for R1. 0.7 looked to be a good value, so we continued using it here. But of course, one may argue that why not use other values? In the case of Aragón Artacho-Campoy algorithm, we have two parameters, alpha and beta. Okay, we have projections are done on various updates. Alpha is recommended by Aragón Artacho and Campoy to be 0.9 and beta to be chosen somewhere between 0.7, 0.8. In fact, okay, when we come to FISTA, then here we have a bunch of other parameters. One of them is the Lipschitz constant here, which we choose 2 for the L2 norm that we are using. Then we have the projection onto B and A of the certain vectors here we consider. What is important here is the update that we choose. When you choose Nesterov, which was the acceleration technique proposed by Nesterov in 1983, then you get the original FISTA proposed by Amir Beck and Mark Tebul. And recently, Edi Atoush and Cabot proposed 2 more updating rules, but they're observed to be making the method even faster, much speedier, at least, I mean, as far as our experiments go. So in the second one, in the first one, we have this parameter T, which is chosen to be initially 1 and then updated in each iteration. And in the first update formula proposed by Atoush and Cabot, we have a parameter alpha. When alpha is equal to 3, then it boils down to be the FISTA. For alpha greater than 3, for example, in our implementation, we tried 17. 17 seemed to be the fastest that we obtained. And the third option, where we have a parameter theta. In this case, theta is any positive number. Okay. So we note that algorithms 1 to 5, we carry out iterations with functions, but we cannot iterate with functions on computers unless they are analog or something like that. So we introduce a partitioning of the time horizon between 0 and 1. And we use Euler's method in the computation of PA in solving the initial value problem. So that gives us an approximations of the functions that we are iterating with. In the process, we define the error, the distance to the solution of U, and also distance to the solution of the states. For n equals 1, we carried out some parametric study, and it is seen here that, well, for that purpose that we had, lambda equals 0.7 seemed to be a good choice for Douglas-Rachford. And for Aragón Artacho-Campoy, we've chosen alpha to be 1 and beta to be probably 0.7. I can't recall that now. 0.7. This is just showing the plot with respect to these two parameters, alpha and beta, where it's evident that, you know, this is like a shell and it's touching here. In fact, you can get the solution in just one iteration if you choose beta to be 0.5 and alpha to be 1 for the specific problem that we were looking at. So it gives some insight, and given this insight, I think we had chosen beta to be 0.7 or 0.8. Okay, then this shows the progression of the iterates. For Dykstra, Douglas-Rachford, Aragón Artacho-Campoy. Well, you may ask the question, where is MAP, method of alternating projections? It's interesting. For n equals 1, MAP is the same as Dykstra as far as the computations that we had in R1. They were identical. So that's why we are not reporting it here for n equals 1. Okay, here we are listing beta. For beta, we chose this 0.8617. I mean, there isn't so much fuss here, but just chose the one which gave the best performance. And it's evident here that the Aragón Artacho-Campoy goes to nearby the solution, let's say, pretty quickly than the other ones we tried. And here we see the error in each iteration. The first one shows the error in U. So here it's around, you know, near 10 to the minus 2. Here it's between 10 to the minus 2 and 10 to the minus 3 for the error in the state variables X. So as we increase the number of nodes, or the grid is made finer in the partition. Initially, we take 1,000 points, and when you make that 10,000, error goes down, and it keeps going down. What's interesting here is to observe what each method does. It seems that Douglas-Rachford and AAC, they converge to the solution pretty rapidly. I mean, we are not showing here the number of iterations in which they converge, but they stop earlier actually than this. Okay, here is the table summarizing these pictures. Here we see that, as expected, as we increase the number of grids tenfold, we get a tenfold decrease in the error. You can see the order going from -2 to -3, -4. The coefficient is the same. And it's something that we observe in pretty much all of these methods. IP-opt, we used it in ample and it didn't do a very good job. So this is a certificate that it's more interesting to use projection methods than the traditional, you know, discretize, like direct discretization, and then finding a big, large optimization problem with a general solver. Here in getting these, well, we set the tolerance to be 10 to the minus 8. So when the tolerance is reached, then the method stops. Here, this gives an idea about the CPU times. It seems to be slow, the smallest in the case of AAC. Dykstra takes longer. IP-opt much longer and not a very good quality image. Okay, the second case we consider is n equals to, things start getting a bit more interesting. So we aim to go from this initial point with this initial velocity, the direction, initial slope upwards, and stopping here at 1, 1 with the terminal slope of the curve given like that. So we want to minimize the L2 norm of the acceleration to get from initial to terminal point. Okay, so here we also show the components of the control U. Here we show the norm of U. The norm of U is A initially, but we are on the sphere. And then we have internal control as also testified here. We are on the sphere initially, and then we go through the interior of the ball, and then we hit the ball surface and stay at the surface. It's possible to prove that we will have only 2 switching points for this problem or any problem in Rn. It will be interesting to look at the error that we are making in each discretization level. Again, just to repeat, the meaning of the discretization here is that when the discretization is coarse, then we are iterating with a coarser approximation of the functions. We are still doing iterations with functions, but functions represented by 100 points in this case. Then 1000 points. As expected, the error is going down, of course, but also the behavior is interesting to look at here. And finally, this is 100,000 points. Dykstra, DR, AAC, and finally FISTA, they all seem to settle at the same point, at the same value, function value, as you make the functions you are iterating with more accurate. But there's something going on with MAP, method of alternating projections. We can explore that a bit more, because here it seems to be giving much lower function value as if it's doing the job. Is it possible? Let's look at the errors in control and the states. You see, there's an interesting thing happening here. The MAP and Dykstra, they overlap exactly here. Almost, it looks to the eyeball, but we need to scrutinize it a bit more. So when I look at it a bit more closely, they really overlap here. Okay, Douglas-Rachford and AAC, they are settling at a lower error. But when we go to the other one, in X, they settle at a higher error. But in both cases, the error that is exhibited by FISTA isn't good. It's not good. So, okay, let's increase the number of points with which we are approximating the function. So we see that here the map starts showing different error. They start separating from Dykstra. And ultimately, when we do these refinement of the discretization points, look what happens to map. Map is given by this reddish. Stays where it is, where it is. But the others go down somehow, doing some meandering. Okay, maybe having a look at this table will explain things a bit better. So as we discussed before, you know, increasing n by tenfold, we expect the error to decrease tenfold. So that's what we observe with Dykstra, DR, AAC, FISTA as well, although their levels are different. So for method of alternating projections, it's getting stuck in here, 5.8, 10 to the minus 2. And here it's getting stuck at 3.8, 10 to the minus 3. And it seems to be getting stuck forever. So this looks like we are observing an example, a nice example of a method of alternating projections having weak convergence. Because this is telling us what's happening pretty much in the function space, because the approximation of the functions is quite precise here, quite accurate when we are talking about 10 to the 4th, 10 to the 5th. Another thing to note here that FISTA looks to be about one order worse in this than the others in general. So that's also surprising to observe for us, because we had never used FISTA before in application. Okay, now n equals 3. We want to go from this point and this velocity. So you can think of a drone or a spacecraft going from one level to another level and keep circumnavigating. So here is the numerical solution. The dashed blue curves show the case when we have unconstrained control, and the constraint on the magnitude of the vector, length of the acceleration vector is 10, so which is much smaller than around 16 here, which it reaches up to. And here we see the reconfirmation of the maximum principle. So we are on the sphere initially, and then we, where do we start exactly? No, we start actually. We are initially on the sphere and then go through the sphere, inside the sphere, and then hit the surface of the sphere and stay on the sphere. So that's what's happening in U1, U2, U3 space. Okay, now objective functional error. It appears that FISTA has worse functional value it's settling at. A map is settling at a much more impressive functional value. Again, we ask the question, what's going on with map? Is it really doing much better than the others? Okay, as we go finer, we get pretty much to the same functional value, but here map finally stays at a worse value. Let's look at the errors in the control and U. Here we can see that FISTA initially, I mean, there is a degree or order, there's a difference of order.
Yalçin, we have less than 5 minutes.
Okay, thank you. 10 minutes, less than 10 minutes. Okay, thank you. I think it's enough for me to finish. Okay, so okay, we can also note that in each of these iterations, the AAC is the fastest. But having said that, FISTA can be made the fastest by applying the Artacho-Campoy steps or updates. And perhaps it's easier to understand what's going on when we look at this table. Again, we see the progression of error, the decrease in error. When we increased n by tenfold, the error is decreased by tenfold roughly for Dykstra, DR, AAC, and FISTA as well. But there is an order difference between FISTA and the other group of methods, except, of course, method of alternating projections. Again, it converges to a point which is not a solution. Okay, so what have we observed? We observed that Dykstra, DR, AAC as a group of methods, they seem to be the most successful in solving these class of problems. The Dykstra is also best in generating optimal states because the error, when you look at the error in the states, it appears as the lowest. So if you are giving emphasis to the state space, that is the curve in which you are constructing, you are designing. If that's most important, then I think it's a good idea to use Dykstra, although it takes longer, as opposed to Douglas-Rachford or AAC. But FISTA, it doesn't give accurate enough solutions in general. Okay, another comment to make is the projection methods seem to be better than standard discretization approach, like using IPOpt and or any other optimization solver paired up with AMPL. And MAP, method of alternating projections, is observed to converge on the weekly for n equals 2 and n equals 3. Interestingly, for the example at least that we considered, for n equals 1, MAP is the same as Dykstra. And the models and algorithms we have here should be regarded as prototypes for future extensions. We are laying the grounds here for other interesting, maybe optimal path planning, optimal curve design kind of problems. Future, okay, the constraint is piecewise linear when we use Dykstra. Then this might simplify further the projection expressions. So we may choose to exploit that. And extension to general linear quadratic problems where the control variable is constrained will be interesting because the setting will be really similar. It's just that the projection expression will be slightly more complicated, but it should be manageable. Extension to non-convex optimal control problems. Well, the success of Douglas-Rachford method is well known for non-convex problems. So why not apply methods like Douglas-Rachford and Aragón Artacho-Campoy to non-convex optimal control problems and see what happens. Thank you. That's all I would like to say.
Thank you, Yalçin, very much for the very nice talks, making us have more motivation to work with projection methods. So now the time for questions. I have the maybe I have the first question. In your problem, A is R5, the set A is R5 subspace, and the set B is a ball, right?
Yes, that's
So
right.
can we set about the Slater condition with A and B? Can you determine if A and B satisfy Slater condition? I mean, if A intersect with
we have a strongly convex problem here as optimal control problem that we have is strongly convex.
Yes, but can we determine if A intersect with the interior of B or no? We know that
Right.
A and B intersect
yes.
B, right?
No, isn't the constraints here looks linear, if I'm not mistaken, in terms of the differential operators?
No. This U minus is piecewise linear in general.
Okay.
Yes,
so we define them here. Okay, so your question is,
so if A intersect with interior B or
yes.
no, is yes. So then
yes, well, the answer is I see. Yeah, I'm just thinking if the terminal conditions are chosen to be in a peculiar way, then no, their intersection may be empty. Yes,
maybe empty. Okay.
but in that case, it also means that the original problem doesn't have a solution, you know, because in the original problem, let me go. I show it. I showed it just here, and then here, yes. In the original problem, if you choose A too small enough, then solution won't exist because you want to get from S0 V0 to SF VF, right? Just a point in the joint space. So if you just thinking of it as a dynamical system where you are interested whether you can get from one point to the other, it depends on A. A is a bit like the resources that you have. If A is too small, then you haven't got enough resources to get from S0 V0 to SFVF.
Yes.
So that's what it corresponds to. So if you know that A is large enough, that is sensible, in the sense that, well, you can get in unit time from one point to the other without any problem, then you are fine.
Okay, but
for the whole problem. So it's to do with whether solution exists to the whole problem or not.
In your numerical examples, how to choose A? How you choose A?
Okay. For example, this one.
Yeah, I. Okay.
I chose to come here because here, for example, if you choose A to be 2.4, then you have no solution
Yes.
for the problem. So you need to have some, okay, I have to answer it in practical terms, in terms of what the dynamical system makes sense. You have to choose A large enough so that you have solution.
Yes.
That's the only thing that I can say.
Yes,
So
yes.
here, when you go below 2.4, then there exists no solution.
And when I increasing the algorithm, we converge faster. Right?
Yes, well, ultimately here for this particular example, when A is bigger than 4, or then it is unconstrained.
Yes, yes, that makes sense.
Because
Thanks.
the solution, I mean, the constraint never becomes active if A is bigger than 4.
Okay, thank you. Okay, any other questions?
Yalçin, can you say a bit more as to why the map doesn't actually converge to the solution? As I understand it, if a solution exists, it will be
Yes.
unique. And therefore map ought to be converging to something.
Yeah, it does converge to something. It does converge.
But it ought to converge to the solution, right? In this case, because there is one and it's
Yes.
unique. So what if it's not converging to the solution? What is it converging to, and why? I don't understand quite why weak convergence would not bring it to the true solution.
It's converging something which is not feasible and get stuck there.
But these are convex sets, so
yes. But
again,
also map is known to converge only weakly. So this can be regarded as an example of weak convergence of map.
But I still, okay, I guess I'm not familiar enough with weak convergence, but certainly if they were strictly convex sets, I would have thought weak convergence would still guarantee strong convergence, right? Maybe somebody else could comment on this.
Sorry, can you repeat, Gary? Can you repeat what you said?
Regina, I don't quite understand why map doesn't converge to the true solution. The problem's convex. I think it might be strongly convex. There's only one solution.
I know, but when it's an infinite dimensional space, you have two types of convergence. One type is strong convergence, which is convergence that with respect to the norm, and weak convergence, which is more like, for example, in a Hilbert space, you will have an infinite sequence. And in a Hilbert space, the weak convergence corresponds to the convergence of each of the coordinates. For example, you may have a sequence to 0, but they don't converge strongly to 0. They converge weakly to 0. So they are all in the boundary of the ball, but they converge weakly to 0. So you may have that type of situation. So it's really very crazy what happens when you generate a sequence that converges weakly. You really you understand that it converges weakly because it does not converge strongly. In fact, what Yalçin maybe can say is that he can certainly say that it's not converging strongly because of the differences of the error.
But you still have it's still a finite dimensional problem. I mean,
no, the problem is infinite dimensional.
But you've discretized it. You've reduced it to finite dimensional subspaces, right? They might be subspaces of continuous functions, but they're still finite dimensional subspaces.
No, the iterates are functions. The iterates are functions, and you approximate them. Sorry, Yalçin, you answer now.
So yeah, the iterations are done in function spaces, but
Right.
you use approximations of functions to do it. You do not discretize the original problem.
But they're finite dimensional spaces of functions, right?
No, it's a finite dimensional representation of the functions. Otherwise, the space is still function space.
Well, sorry, okay, they're
To
finite.
be able, so you do your, when you do your iterations, you have some error because of that. And that's why when you make your grid finer, you get a more and more accurate result in the function space, because you are approximating your iterates to be closer to the real functions. But when you discretize right at the beginning, like replace the integral by Riemann sum, let's say, and replace the ODEs by Euler's method or something, then you have a finite dimensional problem, and you solve it as a finite dimensional problem in finite dimensional space. That's not what we are doing. What we are doing is we first optimize, and then we use our iterations by following the optimality conditions in some sense. By satisfying optimality conditions at the same time as we go.
So the discretization, the choice of n, doesn't restrict you to a finite dimensional subspace of functions.
No. Iterations are still in function spaces, but we do the iterations approximately. Because let me show you the projection here. Yeah, this one. I mean, this projection. Everything here is a function. Like u minus is a function. Okay, you start with some u minus, and then you solve this initial value problem. Suppose that you can solve it exactly analytically. Suppose. Then what do you get? You get this x1 of 1 and x2 of 1 exactly, and you substitute that in here, right? Then C1 and C2 are known exactly, and you substitute them in here. Then what you get is an exact function in the iterate, the exact iterate. But instead of the exact iterate, we are using an approximate iterate. Why approximate? Because we solve this ODE approximately. But approximation gets better and better as we make the discretization finer. And we have no doubt about that because of the theory of ordinary differential equations, right? So this is the method that we apply is convergent to the solution by the theory of the ODEs, like numerical solution of ODEs. So we know that as we get a finer grid, we are going to get a better approximation of the function with which we are iterating.
Okay, thank you for the interesting discussions. Any other question or comment?
I was curious about something, which is that if you go back to the convergence plots, I noticed you have this for FISTA. There are these nice oscillations that that we've observed oftentimes. Yeah, there we see these, and here as well we see these lovely oscillations that tend to typify what's happening when the update that you're tracking, right, which is this shadow sequence, this proximity operator sequence, right, because FISTA is a kind of ADMM, when that thing is basically kind of wandering back and forth across a solution, And of course, I do research on accelerating these things by centering by backwards computing the dual and centering it. But what's kind of curious to me here is your Douglas-Rachford isn't doing the same thing. I see no oscillations for Douglas-Rachford.
There is some, but not as widely as the other one. So let me go back to the description of FISTA again. So we use this Nesterov update. So if we use the second one with alpha equals 17, for example, or whatever, 18, 20, then most of those oscillations disappear somehow. I don't understand why. And it converges a lot more quickly. In fact, either with the second one or the third one, you get a much faster convergence than the other projection methods. But the quality of the point that it converges is not as good as the other ones, one might argue. Anyway, going back to your question again, depending on which, if you use the second or third updates, those wild oscillations seem to disappear for this example. Maybe it would be interesting, Scott, if we apply your approach.
Well, my guess is that by changing that alpha, because I recently refereed papers that have basically looked at this, where they've built the Lyapunov functions for algorithms that are splitting methods or related to this, and then they change the constant, and rather than have something that circles around, they end up with something that just sort of turns sharply and drives right into the solution. And then they show that for this problem you pick this alpha and it does it, and for this. So my guess would be that probably that's what's happening when you change that alpha. I don't know, but that'd be my guess. Anyway, thank you for an interesting talk.
Thank you, Scott.
And also an interesting discussion. I've never thought about this difference between, and I don't fully understand it, but I look forward to understanding it better, this difference between having an infinite dimensional problem with these finite approximations versus having a discretized finite dimensional representation of an infinite dimensional problem. It sounds magical, and I appreciated listening to the conversation and being confused by it.
It's intriguing, I would say, intriguing somehow. I mean, it's, yes. Anyway.
Okay, thank you.
Thank you.
Thank you. And thank you, Scott. And yes, I hope the situation of COVID-19 in Hong Kong is still good. Because I see you have masks even now.
It is. I'm in the office, and so I've got the mask on. It's very good. I think all of our cases for the last couple of weeks have all been imported and caught at the airport. So life here is very normal, which is why I'm in the office.
So you are very careful about that.
Yeah.
Okay, and thank you all for joining us today. And yes, the talk of Yalçin will be available on our website. And Yalçin, please send us your slide, and we will put it on the website as well. Thank you very much, and see you next week.
Thank you very much all for joining.
Thank you, Yalçin.